Hi, everyone. Welcome to another Haskell study group. I'm your host, Ron Baden with Atlanta Functional Programming. To my common list study group members from yesterday, my apologies. We were having some discussions yesterday, and we ended up not having particular topics for a stream. Stay tuned for next week for new topics in that regard. Um, just a couple of other announcements related to AFP. AFP is still looking for speakers. So if you are one of our attendees or patrons that are out there in the virtual world and would like to give a virtual talk, please free to ping me or my co-organizer Judd. Um, I'm available on functional programming Slack, has Bugram, as well as the Discord, the Lisp Discord server has Bugram as well. You can also contact me if you're interested in giving a talk by giving me a DM on Twitter. My handle is Unix Nerd, uh, UNXN3RD. Feel free to contact me in any of those avenues. If you have a particular topic, we are welcoming any topics whatsoever related to functional programming or architecture, application of functions, and so forth. So whatever topic you come up with, let us know, and we'll schedule you. AFP is still in limbo in terms of our in-person meetups for those of you who are in the Atlanta area. So for the time being, we are still somewhat doing virtual presentations. If there are people in the Atlanta area who are aware of any venues or something that we could use to potentially do a presentation or a talk on, I know things are opening up, but different places have different restrictions. Feel free to drop us a line too as well in that regard too. Last time we talked, and this is a couple of weeks ago, we were introducing the concept of the monad, and I kind of gave you somewhat of a semi-thorough overview of what we've covered thus far, semigroups, monoids, functors, and applicatives, and gave you an idea of what monads are, all about. And this includes a discussion of the do syntax, as well as using the sequencing operators, either from applicative or monad, to actually go in and sequence operations in order so that one might be able to then um, go ahead and do what do syntax does. Do syntax is nothing more than syntactic sugar around the sequencing operation combined with bind. We also introduced the concept of bind, which is nothing more, if you really want a simple sentence on it, is a form of concatenative map. All right, it will fmap your using your applicative instance on your particular um, uh, monadic type, and it will then join subsequently the intermediate results that are collected, because when you fmap a function on top of monadic type, you get a monadic type of monads. All right, so you're adding structure into the mix, and what bind does is it flattens that structure before moving it along. We saw that kind of example when we used bind to do something along the lines of grabbing a line from standard in and passing it to uh, put string line, where if we just do this, you'll end up seeing that it will return type of this is going to return an IO unit, which is actually the return type of string line. And it does this in a top down fashion, right? And left to right fashion. Okay. This is actually following um, the IO. So bind actually tends to follow. and is similar to a lot of things that IO does, and that's only because the bind operator was a generalization of stuff that Haskell did with the IO type. Today, we're going to be discussing the monadic laws. That is, when you are designing and defining monadic types, what laws do you need to preserve? Because, as I mentioned, the monad laws, the the monads type class is another type of type algebra. All right. And it is just a type class that you have to define an instance for your specific user defined type that ends up um, uh, uh, being monadic. All right. So what I mean by that is when you're defining your instance of the monadic type class, just by defining the implementation for say bind, it does not necessarily mean that you are by definition a monad. Although from the type checker's point of view, it might look like that. All right. As I mentioned before, for all the other algebras that we covered in our discussion thus far on Haskell and what the book covers too as well, um, monads, the monadic laws aren't actually type checked for a particular instance of the monad type class, all right, at compile time. One way to ensure that you are preserving those laws, and we'll be discussing them in a minute, is again by using quick check. And if you're using the checkers library, you will get your standard quick check rules for free, all right? And we'll see an example of that in a minute. Finally, today we're going to be discussing, time permitting, um, have a discussion on uh, just covering a couple of examples once we go through the monad laws and go through some examples on application and composition. All right. Has with all of our discussions, if you have any questions whatsoever related to any of the material we covered thus far, or even today's material, feel free to drop it in the chat window, and I will address them as we go on, go along. This is a very informal discussion, so go ahead and um, drop any of the your questions in there, and I'm more than happy to answer them. Okay, so let's begin with the monad laws. Okay, the monad laws actually come from a lot of stuff that we've seen with associativity. Sorry, with the applicative type class. Recall the applicative type class having you know a the following laws, all right? Identity, composition, homomorphism, and interchange, right? Of course, we've gone through this enough times in past discussions. I encourage you to go look at those past discussions for more information. But the monad laws are going to look very, very similar to this, okay? What do I mean by this? Well, monad has this notion of identity first off, and this is not just um, normal identity. It has both right identity and left identity. So what does right identity look like? Okay, well, right identity, given that again, the minimum implementation of the monad type class is the bind operator. The right identity basically is that given a monad, all right, bound to a return, you will end up getting the monad, or the original monad itself, or a monad M, okay, a monadic instance of M, all right? Left identity is much the same way, all right? If we look at left identity, you have essentially a function that calls return. Return, remember, is kind of like pure in the applicative type class in that it lifts whatever value is passed into it into the monadic world, and then this result is then bound to some function. Sorry, and that will return f of x. All right. So you could think of that as doing again a f map combined with a join to get you a result, the f of x. Okay, we could see that this is the case. All right, that this is a pretty straightforward application of the monad the bind operator, just by simply revisiting what the bind operator actually looks like. Okay, recall that the bind operator, all right, is a function that takes something that's restricted on a monad M, and it returns a two argument function, one that takes as the first argument a monad instance holding a value a of some type, and a function that takes the a and returns a monad of type b. All right, and it will then return a type b. Remember, this is nothing more than um, the the applicative with the arguments flipped. All right, the applicative apply operator with the arguments flipped. All right, and obviously this is also the same as a f map, right, with the arguments flipped as well, if that seems a little bit more um, familiar to you all. Take whichever analogy that you will. The point is, the arguments of passing the value first and then the function are flipped around. This actually brings up what I was talking about earlier, and that is the bind operator being this left to right applicable sort of function. Okay, then right to left, which is what most people sort of associate with function applications, and it comes from this generalization of the do syntax sugaring and sequencing that was done when they were generalizing some of the stuff that they were doing with Haskell IO into a more formal type definition with the type class, right? Um, Recall also what return actually provides. Okay, return is actually doing this lift operation, much like pure from the applicative side. Okay, if we look at right identity, all right, just to take the example of right identity for this. Okay, what it's doing is um, it is first actually excuse me, I had something in my throat. Um, it's essentially taking a a monad M, all right, unwrapping it, all right, grabbing its value and passing it over to return, which again lifts it back up into the monad, the original monad space. Remember, return doesn't do anything but take the monad. It inherits the monad that was passed into it originally. All right, and it will go and associate whatever that monad is, and make sure is that whatever comes out of its constructor is an instance of the original monad, all right, that you passed in. In this case, what the Haskell type inferencer is doing is it is uh, taking up the monad, unwrapping it, passing it over to return, and it infers that since M is some monad, in monadic instance, let's say the list monad, for example, and again, we're going to address this when we look at uses of monads, it will assume that return must have to return a list monad. If this was a state monad, it will return a state monad. If it was an IO monad, it will again return an IO monad. Okay. But the bind is doing behind the scenes is it's unwrapping through the join operation the value that is inside the monad. based on the rules that were implemented for that particular type. This is a very important thing to recognize. Bind's rules for unwrapping, for joining, okay, because remember, it's a join, an F map followed by a join, okay. Those rules are defined for a given type, all right, which means different types have different rules for how you join. If you define a type and you want that type to be monadic, you are defining the rules on how fmap composed with join should work. All right, you are doing that, writing those rules. Okay, once you do that, everything is golden. You'll be able to actually work through this, and but recognize that this behavior of bind, the only thing you need to know about it is this property, this mathematical property. All right, that given bind being logically adherent to the identity property here, you know that when you are taking an M and you are binding it to a return, you're doing a right identity and it'll return the original monad. The same thing goes with left identity. What is left identity doing? Left identity is saying, okay, given a value X, okay, lift it to whatever is required to pass it to a function f, okay, uh, that's going to be used for fmap, and it will then um, take that lift and apply the function to it internally, and it will return the original um, value uh, applied to that function. All right, you'll get the f of x. Okay, so why is this actually an important part, different than what we said before? Well, the first one, we're wrapping it. Okay, we're taking a monad, we're returning it, which means we're lifting the value again, and we're going to get the monad back. That's right. That's why right identity is important. Left identity is important. Is given a a function, okay, f, that may take some value, and um, it and you're taking in a monad of that will return um, that value to f. It's going to go and unwrap it and just apply the function to the underlying value. So this is why you could do something like this, even though this I don't know in what case you would end up doing this. You could take this, and I think you could just simply pass it to this. Did I? Uh, Hold on. I must have messed something up here. Um, Let me try this again. This is let's say that we do, let's see, double equals 2 times x. What is type double? So now let's do return uh, um, do this? No, it wouldn't. We'd have to do fmap. Um, let's see this. We're gonna have to take in the list. So let's do it a slightly different way. Let's say double list, and let's say that we take an x and we return the list 2 times x. Okay, that's just simply double. All right, type double list. Okay, and let's see if I could just do double list. There we go. So you can see that provided that f, okay, is taking in a function that requires some monadic type, okay, what return does, again, does what we did with the right hand side. Okay, it's taking the return the type that it inferred that uh, um, is expected, and it will actually lift one to that type. So in this case, double list is creating a list. So now the entire pipeline now is going to become a list. All right, it'll be a bunch of list transformations. Okay. So return one becomes a list. It goes into the bind, which will unwrap it. And when it's doing the fmap calling double list, it creates a list of lists. All right. So this actually will create an intermediate form first of two, and then it calls join, and join will actually create will unwrap one of those layers, and you end up getting two in return. Okay. This is why left identity works. All right. So right identity talks about returning what was already given to you as an input. Left identity talks about given something that's going to return a specific monadic type. We're able to lift any set of values into that monadic world and then move it and push it along in the transformation process using the bind operator. Okay. The other property, again, this is nothing more. What we just saw here is really a reiteration of what we saw with applicativity, honestly. Okay. I encourage you all to go through the exercise, uh, or watch our older videos on applicative, and recognize that this left identity, right identity stuff that we see with um, Monad is straight out of applicative, and it really shows that Monad essentially influenced applicative. Applicative came again. Remember, applicative didn't come first. Monad came first, and when they recognized this algebra, they were able to move it out to being its own um, algebraic type. All right. The second thing that is that's a monadic law is associativity. Again, this again falls out of applicative too as well. Applicative, we've kind of gone through this, but there's a slightly different rule with the associative law. Like if you see here, we didn't actually explicitly talk about associativity. We just assumed that it's going to be associative just merely because of the fact that it has to be monoidal. All right. Because applicatives are monoidal functors and monoidal operations have to be associative, you can work through the logic here, but you can see that it will clearly be associative from that property there being defined correctly. All right. The associative law for monads, though, basically says if I given a monad M, okay, if we try to bind M to some F, all right, and then bind that result to some G, okay, so G takes up some sort of monadic type, returns either a monadic type or some termination condition. F takes in a monadic type and probably adds and returns a monadic type. So it's adding structure. Each layer is adding structure. Okay. This is the same as if we took an M, all right, and we bound it to a anonymous function that took the value x, because remember when the bind internally calls fmap, and when fmap is called on a function to a structure, it's going to first look up the functor instance, see how it's defined, and use that rule to go and unwrap the layers of the type to push it along. All right, and this is kind of the same idea. So we're going to get a value x in this anonymous function, and we're then going to apply x to f, or we're going to apply f to x, and take that result and then bind it to g. Okay. So what this is basically saying here is is whether or not we do this, we can do this somewhat eagerly. And what I mean by eagerly is we're applying each function individually, or you can actually just create a function that takes the piece of the transformation chain and apply just do the bind on the external once. All right. Either way, you're ending up with the same result. You are going to end up with the same exact result, which is really the return type of the monad that m or all the transformation functions are going to return. All right. I am going to pause for just a moment, and I'm hoping that this idea is uh, makes sense. All right. But I'm going to pause for just a moment just to see if there are any questions. Okay, it looks like we're good. Um, all right. So again, you don't have to necessarily um, uh, you don't have to necessarily build these checks yourself, right? Thanks to checkers, um, we can actually go ahead and get from data.monad, right? Import test.quickcheck. Like I could just copy and paste some of these here because I don't think I need all of them. Okay. And we could just go ahead and create a main function here that get the IO right. It's IO unit main equals, and let's just say quick batch on some monad. And let's go ahead and say it's 1, 2, 3. Okay. So we're basically testing the list monad just to show you that this is available. All right. So we just reload. Data.monad is not available. Hold on. Let's see if this actually works. Um, um, interesting. I thought data monad should be available, but we will try this out. Quick batch monad 1, 2, 3. Let's do. Let's see what this does. Use dash v. Data.monoid, data.kind. Data.monad is not available in. Interesting. Okay. So this doesn't. Ambiguous type arriving from the use of monad. I may have. Hold on. Let me go look at something. Maybe I'm missing a dependency in my test.cabal. Okay, that's the reason. We need to do test dot quick check dot attic. Okay, let's do that. Use a type intention specifying all three. Okay. I'm going to add this test later here in just a second here. Because I'm wondering if I don't need to do this just to get the includes right. Because this should work as is, but for some reason it is not doing what I expect it to do. Okay. Now let's do this quick batch monad 2, 3. Okay, for some reason this seems to work on the command line, but when I try to pass in the quick check properties, it's not working as I expected to. I think it's because, oh, got it. Well, I need to probably actually explicitly say that I'm importing this from. And let's try this again. As you can see here, for folks who are following the stream along, this will actually test to make sure that that all the properties that we just talked about thus far are correct. Obviously, with associativity, they're being a bit more rigorous. The one thing that you may have noticed is it is actually doing not just associativity, but it's looking at pure. That's because of the fact that um, because applicative came after monoid. Sorry, because applicative came after monad. Yes, it came after monoid too as well, but it came after monad specifically in terms of our discussion. It is actually verifying that not only do you preserve the properties of the monad laws, but you're also preserving the properties of applicative. So it's guaranteeing in sense that you are both a monad and an applicative, which I thought was pretty cool. Um, let me see if this fixes my issue here. And does not export monad. Interesting. Okay. Let me do this. Yep. See what happens here. And the expression one. That should have worked, but for some reason it's not actually triggering this. Let's see here. What is causing this one? Because this is correct. Let me see. Do I? My apologies, folks. I'm just trying to see what I might be doing wrong here to get this into a property factor that we could then leverage. As part of a test that we could then leverage, that is. Let's see here. main do. Okay. Let's do. Okay. Okay. Maybe this might be. Okay. Let's try doing this. Um, just to make things a little bit more interesting. Do let data equal uh, let our data set equal be specifically something that takes in 3 integers. It might be the fact that we are actually defining a type here that's properly creating an ambiguous type. Let's go ahead and create this to equal this. And let's do actually we don't even need to do that. Let's just say this. And let's make this a proper list. Let's see if this does not cause any issues. Ooh, okay. Now we will actually see if we run main, monad law is being run, and it's going to again run through what we had before. So the problem is we're getting some ambiguous types. So one way of addressing that is essentially saying, okay, I'm going to explicitly tell you that this type is a list that contains 3 integers. Well, it's a list of tuples where each coordinate in the tuple in the triple is going to be an integer. So this is all great. This is like in the perfect case of obviously when we are dealing with a a monadic type that is perfect, really, because again, we did not define this. This has been defined. It's been tested. It's a well-tested monad. All right. It's the list monad is, and we're going to see more examples of the list monad. I'm not going to show more than what I just showed you here, right, for the time being. But we haven't actually seen um, how this works in designing a system, right? So let's go ahead and go through this example that was provided in uh, let's create an example of a bad monad, right? um, say for example, and this is straight up from an example that I found that was in the book. Let's say that you have some sort of data item, okay, type of A, all right, that takes an A, and it is just nothing more than uh, generating, this is similar to the example in 18.5 for folks who are following along, all right. Um, and this is driving EQ and show, okay. Now, given this data item, okay, the reason why I named it that is just because I it, I didn't like the names that were provided in the book. To be quite honest, it doesn't show what exactly we're talking about. Okay, um, given this this type, let's say that we define our functor instance, okay, for data item, and where we define fmap of some function that takes in a data item of IA. And what this is going to ultimately do is uh, provide you as the first value the count of the number of items that this particular item is constructing, and or number of times that it's actually being called, and the function applied to the actual underlying value, right? Pretty simple. We all know that this structure here of data item with the first value is fixed is very similar to when we specialize the applicative on pair. So I encourage you to go to look at that if you need some help on understanding that. Now we're going to actually use this advantage here and define also an instance of applicative, on a data item where, and then we're going to define pure being nothing more than this being called 0 times, and we're going to be saying that um, the applicative or the apply operator, where you're given a data item of n for a given f, and you apply it to a data item of, n prime given some value a, and what we're going to do is we're going to say that this is going to be nothing more than the number of times both the function is called plus the underlying data items count, and this is going to be the result of the function applied to that value. All right. So this is all well and good. We've seen what we need this as far. You may be wondering why I'm defining function or applicative when I talk about monads. Remember when we talked about monads in general, in order for monads bind operation to work, you need to have the apply being available to you. And in order for apply to be available, that means you have to define the applicative instance. And if you're defining the applicative instance, you need to have fmap. And if you're going to be defining fmap, you have to go define a functor instance for it. So this all connects everything that we talked about thus far. All right, just follow along on it, and it becomes pretty straightforward. All right. If you understand functors, you understand applicatives. This monad structure that I'm doing should be pretty mechanical by now. And you're just defining the rules for your particular type class instance. All right. So in here, we're going to go ahead and define a monad instance on data item. And where, and we're going to say that, again, um, return is going to be nothing more than an alias to pure. Remember monads instances there. Um, this basically is an alias to the applicative function that we're going to be doing, but we're going to use now, data item, some function, and we're going to bind it to some function f. Okay, remember this is this bind operator to some function f, and what this is doing is nothing more than taking, the cases that we have, all right, that we created. Let um, data item being +1 to the property b, and what we do is now um, we're going to essentially define an instance of uh, the generation of creating random instances, right? How do we do this? Remember when we talked about quick check before, to test this monad, we need to go and define something in order to create random instances of this type, this data item type. For this, we have the arbitrary type class as being part of the quick check library, and we're going to use that to define a arbitrary specialization, and we're going to specialize arbitrary on top of data item of A, and we're going to say arbitrary is going to be equal to nothing more than data item composed of arbitrary applied to um, some arbitrary here. So we're generating an arbitrary integer for the first argument and an arbitrary integer for the second argument. This apply operator is nothing more than creating a partial application, and then this is then lifted into the data item space and used to apply to the secondary argument. All right. Remember, for folks who are looking at that and scratching their heads, Uh, what was it? Sorry. This is nothing more than fmap. Um, so we're fmapping data item on arbitrary. All right. Creating data item, lifting it up, making it data item arbitraries, and then applying that to arbitrary. All right. This will generate um, a set of random data item instances. Okay. Now, we're using do. You don't necessarily need to use do, but we're using do. All right. Let's say that we create a data item of integer string. I don't like using int for this time being, but you can also call it int. The book uses int. All right. Um, let's say that this guy is undefined. All right. Let's do quick batch on functor. Make sure that it's a valid functor. Let's then do quick batch on applicative to make that it's a valid applicative. And then let's do quick batch on monad to make sure that it's a valid monad. All right. What you're going to see here is when you reload. Um, ooh, that's the reason. A local variable here in the bind operation, right? Just a all right. R trigger blah 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 blah. In a statement, do quick batch function trigger the expression. Name my function second argument. Do let. Oh, I forgot to define one more thing, which is, did I forget to? Yes. Okay. So this will not work without having one more particular instance defined for this type. And that is, we need to figure out a way in order for those properties to be tested against, we need to define the equality operator for on our data item type. So in order for we to do this, we need to go and define, given EQ of some underlying value A, the EQ prop that's part of quick check for the data item specialized on our value A, where, and we could just simply, for the time being, just say that our equality property is just an alias to EQ, and then we'll let the top level functions to actually go in and, um, those are just going to be parametric functions that will end up um, working themselves out whenever we need to. All right. So now we have this, okay? Um, this test is going to show that we have an invalid functor and an invalid monad, right? Why, why am I saying that? Well, you can easily see with functor um, that identity will fail, okay? Um, just on a simple case, okay? Um, and because applicative depends on functor, applicative technically also failed. So although we pass applicative's properties like flying colors, because we can't actually apply anything because it's not a monoid, it's not a proper functor, this function also fails for this input data item is input. Okay. And the reason why it's failing is um uh simply because of fact that the monad instance that we define for our count me doesn't actually, well, our functor instance first off doesn't appropriately define identity correctly. You could look at this right now and you could see that um, this is already violating uh, stuff incorrectly here, right? Um, Specifically in that this identity thing is not is because we're incrementing the count on the number of calls to data item. Um, when you pass in identity to this fmap, um, and you say one some value x, you're going to get two some value x, which means you broke an identity. So the way to fix functor is pretty straightforward. This is nothing more than taking this and saying data item I f of a. Let's go and check that now. Did we fix functor? Um, I'm going to show you in a minute that you could also, if you really wanted to, the book actually shows examples on how to break it completely, including applicative, like really make applicative break. But I really encourage those of you to read, for all of you to read that section, just because I don't really want to repeat um, what's already in the book for that. So let's see that we reloaded it. Let's go ahead and run our tests here. Okay, so now we have a valid applicative and a valid functor, but we still have a broken monad. Okay, how do we fix monad? All right, to fix monad, we need to start thinking about what exactly is what exactly is making um, uh, the monadic instance invalid. All right, and one just merely has to look at the uh, the data item passed into F in the bind operator to get what the same idea is before that we had before. Okay, and that is again, in order for right identity and left identity to work, we can't just increment the function. We could just simply do this, and this, if we reload it, should I miss something here? I may have missed one case here. Um, every tests. Yeah, I missed one more test here. Uh, right. The reason why it's failing is because we're not actually applying the function correctly. We're not actually defining it the same way we defined the apply operator. This needs to exactly match what you're doing inside the apply operator, because bind is doing an apply and then doing a join. So if we do that, if we do this, oops, um, do this here, uh, here, okay, reload, good. Let's do our test, and we're good. Okay. So let's recap here, just to understand what we've just done here. Right identity and left identity, the results of which of those have to match exactly what you would do if you had to if you defined applicative yourself. All right, that is something that again you have to define um, yourself, and then you can use those aliases this way. So like for example, this bind operation, as far as I can tell, we could simply just also define this as, uh, actually, I'm not sure, but since it is a valid applicative, this should work. Um, do this. Um, yeah, this is going to be doing this. Data item n prime on F applied to data item n of A. I think I could just do that, and this should also work. Um, that did not. Why not? Let's see. How could we call the applicative on this and be? Would this actually just work if I just say? Oh, right. My apologies. I have to also specify it like this. An item is applied to too few arguments in the equation, blah, blah, blah. Okay, that's right, because it's not the same signature. Shoot. I was hoping to show you that by just simply using the bind and, the apply that we had earlier, we could address this situation, but there's no clear way of actually wrapping this guy. Um, at least I would have to think about this just to figure out how to drop this, and that would actually um, clear this thing up. Um, the last topic I'm just going to briefly mention here. I know we're just doing an hour tonight, but it's really because this material I wanted to kind of spend a bit of time to without rushing it. Is composition. Okay, we've talked about. Um, you know what? I take that. I take that back. I'm going to go ahead and hold off on this, just because this is another topic that's going to require a little bit more uh, discussion. So next week we're going to actually finish our journey of monads. Um, I know you guys are probably like, well, why are you, pushing this off a little bit of week? But I really want us to go through and understand, and I at least want to make sure I understood the function application composition and the monad examples, because this piece here, I think, will take you quite a bit of time to quite understand. It certainly did for me. But it's a pretty straightforward thing. If you just really think about everything that we talked about up until now, all right. If you just work your way through from semi-groups all the way to today's talk, you will end up recognizing monads was not just building up what we've done all the way up until now. All right. So tune in next time, and I wish you all a good evening.